This is the first presentation of two on reactions of alkynes. Reactions of alkynes. Alkynes being carbon-carbon triple bonded functional groups where we have just pi electrons like with alkenes to use in reactions with electrophiles such as Br and Br2, or an acid will need a catalyst with water. We can also have use of the hydroboration oxidation reaction, just like we did with alkenes. We can have anti-Markovnikov addition of water, so having acid catalyzed addition of water for Markovnikov addition, and we can have the anti-Markovnikov addition of water. We can also have just addition of acids with alkynes, just like we had with alkenes. There is one important difference with these polar reactions, these first three of alkynes, to remember. And that is that we need to remember that polar reactions of alkenes typically go faster than polar reactions of alkynes. It's not so much that the pi electrons on the alkynes aren't more reactive, higher energy. It's that the intermediates are even higher still. So the intermediates tend to be a little bit higher in energy for these alkynes, the intermediates that are formed in the reactions with acids or the reactions with Br2. The intermediates tend to be really high in energy, and it causes alkynes to be a little less reactive to begin with than alkenes. We'll look at, as we start this first presentation of alkynes, a unique reaction of alkynes over that of alkenes. We have similar reactions of alkynes to that of alkenes, but we have a unique reaction of alkynes to alkenes if we have a terminal alkyne, meaning with a hydrogen off of one end of the triple bond. That's called a terminal alkyne. There's a unique reaction we can have with terminal alkynes that we can't have with terminal alkenes, meaning a alkene on the end. So we're going to look at that in the first presentation here. And in the second presentation, we'll look at those similar reactions like these that I've pointed out. Hydrogenation of alkynes, either partially or this going on to be fully reduced with hydrogen gas and a metal. Usually we'll have a metal that will catalyze the hydrogenation of an alkyne. And we can see even here that this is a syn addition, just like it was with metal catalyzed hydrogenation of alkenes. But we're actually going to find there's a way to have a anti-addition to form a partially reduced form of alkyne to alkene. There's a way we can have these on the opposite sides. We'll show that in the next video. And we'll also look at ozonolysis. So we'll have some similar reactions in the next slide or in the next presentation. But I'd like to cover this unique reaction. First time ever we're going to have a base come in and attack the alkyne. Typically we've had the alkyne going out and attacking the alkene, sorry. This is the first example of where we have an alkene or an alkyne being attacked. Usually again with alkynes and alkenes, pi electrons go out and make their attack on Br protons in acids, making an attack on the metals, I guess, making an attack. Maybe hydrogenation is a little different, but typically these alkynes have gone out in polar reactions to attack. This is a first example of a polar reaction where the alkyne is being attacked. Let's look at that unique reaction. I guess before I do that, I just want to mention we will come back to the star diagram as we close our discussion on alkynes. Just like we closed our discussion on alkenes, we closed with a star diagram or a spider diagram. And I'll point out the notes that are, I guess, needed for discussion of alkynes with acids and acid HBr with peroxide. We have particular notes about the regiochemistry and the stereochemistry. So be listening for that as you listen to these discussions on the particular reactions of alkynes in the second video. The unique reaction is not on this star diagram. Before we get to that unique reaction where the base comes in and attacks an alkyne, we do want to go through some naming. So I just went ahead and had this brief slide here discussing naming. We always, like with alkenes, if that's the only functional group we have, an alkene or an alkyne, we circle that alkene in the longest chain. We've circled the alkyne here in the longest chain. This is a hexyne. Hex not ene, but hexyne, where we note some things. We have a group at the second carbon in from this end, and this doesn't have anything off of it, so the numbering for this parent, this hexyne, starts here. 1, 2, 3, 4, 5, 6. So we have a 2-methyl being off the 2 carbon, and we have a 3 position for that alkyne. So we can start noting where things are. 2-methyl, 3-hexyne. 2-methyl, 3-hexyne would be the name of this. This being a cyclic structure, we know we're going to have a cyclohexyne, so let's count the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a cyclodecine, dec meaning 10, yne meaning we have a triple bond. And in numbering, we number so that this has the lowest number, this branch, but the 1 and the 2 has to always capture in ring structures the triple bond, like it had to capture the double bond in alkenes. So we have 1, 2, 3, 3-methyl cyclodecine. Now we don't have to note the position of the yne in the ring because it's always implied that it's between the 1 and 2 carbons. As you went to name it, you made sure these were 1 and 2. All right, so that's an example of naming that we need to know as we go into the rest of these videos. Now let's get to this unique reaction of alkynes wherein the alkyne is attacked. It comes out of this property of alkyne that is unique, wherein the hybridization is changed as we've gone from alkane to alkyne, from a carbon on the end in an alkane that's sp3, having 1s and 3p orbitals mix in the hybrid orbital that holds these 3 hydrogens. The sp3 hybrid orbitals off the carbon are used to bond to the hydrogens. In alkenes, we know that the pi electrons are the ns site, but we also need to remember that the carbons within the double bond, the carbons here, are sp2 hybridized, and all sigma bonding off of them uses those sp2 hybrid orbitals, where we have now the mixing of 1s and 2p's, so the energy is a little bit lower for the hybrid orbital compared to the sp3 hybrid orbital. The energy of the hybrid orbital is a little bit lower. And lastly, we come all the way down to where we have a s and a p mixing in 50% characters of the s and the p. Then the hybrid orbital has even a lower energy because it has more s to p character. S orbitals being lower in energy, p orbitals being a little bit higher. So with 50% s character and the sp hybrid orbital reaching out to grab this hydrogen, the bond strength is greater, but that's due to some polarity here. We have a little bit, not a lot, of polarity with this carbon. So I'm going to, it hurts to put it in, but because it's very, very small relative to polar functional groups like oxygens and nitrogens, but we have a little bit. So we have an increased acidity. Even though this bond strength is stronger, it's due to a little bit more of its partial, or its ionic character, not just covalent character. Yes, that's a lower energy hybrid orbital reaching out, that's a strong bond, but we have a little bit of ionic character to that bond. The bond distance is shorter, of course, because it's a stronger bond, but just remember it's a little bit ionic, and we can kind of then key in on that and use then strong bases, not just a weak base, but a strong base to rip these alkyne protons off, terminal protons. So before we do that, I just wanted to use this time to also talk about not just properties of alkynes unique from alkenes and alkanes. These are acidic enough to have some unique reactions over that seen for alkenes and alkanes. These don't do that very well. But I do want to note that all hydrocarbons, alkanes to alkynes, are typically low density, so they float on water, water being a higher density, and they don't dissolve well in water. If this is all we have is the hydrocarbons, because of the weak intermolecular interactions. And in general, we need to remember that with alkanes through alkynes, you generally have very weak nucleophilic sites, even with alkenes and alkynes. They're a little bit weaker as far as an attacking site to start from, because you're using bonding electrons. And even the electrophilic sites are very weak, because there's not a lot of polarity to this bond. There's a little bit. And then lastly, the alkenes and alkynes are certainly more reactive than the alkanes, because they at least have pi electrons that are in higher energy orbitals. The bond's easier to break. The sigma electrons in alkanes are very difficult to break. They can be broken, but it's not going to be typically in a polar reaction. You're not going to see alkanes in a polar reaction. We can push on these two with a little bit of oomph. We can use some strong acids, strong bases, but you can't even use strong acids or strong bases to make alkanes really react. There's not much that you can do with alkanes. And as we close, just remember inductive effects. That's what we've really been leaning on here. The electron density in the sigma bond is shifted towards the carbon. This shifting of the electrons from this hydrogen to the carbon because of inductive effects. The hybrid orbital here is lower in energy, more electronegative than it was for CH2 or sp2 hybridized carbons or sp3. We've been increasing in electronegativity due to the hybridization differences of this carbon versus these two. It's more electronegative, pulls that electron density inductively from that hydrogen. Let's finish then and I guess look at this unique reaction because we have this partial positive charge, very small partial positive charge. What can we do with that? Well, this is then a weak acid, pKa of 25, so it's very weak, but we can use a very strong base, amide, nitrogen not being as electronegative as an oxygen, is a very strong base, unstable. We can take and rip that proton off to make an alkynide, make that pronounce the Y there, alkynide anion, where the carbon now that was with proton is now negative because it's lost the proton. He has a lone pair in a sp hybrid orbital still. This is in an sp hybrid orbital, sticking straight out from the line of the atoms within the alkyne. And we have made ammonia. NH2 minus has gone to NH3, and the pKa of ammonia is 36. So this reaction favors formation of the alkynide anion because the pKa of ammonia is even higher. It's even a weaker acid than what we started with the alkyne. So we can show that this reaction favors the right side by going to the higher pKa side. We always go from lower pKa, weak, stronger acid, to the weaker acid. They're both weak, but he's even weaker. So we go from the low pKa side. If we have a solution of an anion and a neutral, we go ahead and propose the acid-base reaction, and if the pKa of the conjugate acid is higher than the pKa of the original acid, then that reaction favors product. If it had been the other way around, the pKa being higher over here and this being lower, then the reagent side would have been favored. And the rule is the acid with the lower pKa, that's over on the left, will react with the conjugate base of an acid with a higher pKa. So the conjugate base of that acid with a higher pKa. We're going to favor the right side. Well, golly, we then have a unique reaction. Surprise, surprise. A strong base will force not alkanes or alkenes, but alkynes that are terminal to act as an acid. That's the first time we've seen in polar reactions where an alkene, or we'll see later with other reactions of alkynes, usually our alkynes or alkenes are going out to attack electrophiles. They're bringing it. As we'll see, there's a lot of reactions you need to learn for alkenes and alkynes wherein we attack an electrophile. We've already seen those for alkenes. We'll be seeing those reactions here in the next presentation with alkynes where they attack electrophiles. But this here is unique. This is unique to the alkynes. Attack of the alkyne with a strong base. Somebody coming in and attacking them. Alkenes and alkanes don't do this very well. So let's look at an example reaction. And we'll be done. So we can take the alkynide anion that we formed and react it with methyl bromide. So this is just a methyl bromide where we do not have the chance for E2. If you circle this CX to kind of note what you're going to attack, I can attack the carbon in sp2 reactivity, but I do not have a beta proton to attack. So all I can do is have SN2 chemistry, and we can make what we call an alkylation of the alkyne product, alkylation of the alkynide, I'll just kind of pronounce that again, alkynide anion. We can have a reaction to alkylate the alkyne, where we have the carbon with proton ripped off using a strong base, and then in the second reaction we have the introduction of methyl bromide, and we can now make a alkylated form of the alkyne. So we're just showing the mechanism down here. This is of course the transition state for any SN2 reaction, where this is just simply acting as the nucleophile and this is simply acting as the leading group. Well, that's it as far as this unique reaction of alkynes, terminal alkynes, with strong bases, so that we can, in the second reaction, use those conjugate bases formed from the alkyne, the alkynide anion. We can use that to attack alkyl halides. Now, of course, we can't attack secondaries or tertiaries in this way because that'd give it E2, because these are strong bases. So we typically use methyl or primary RXs for this alkylation reaction. Of course, if we used a more hindered alkyl halide, SN2 would be, I guess, no longer the favored mechanism. It would be E2. So we have to limit what RX we use to alkylate the alkynide anion. We have to use methyl or primary RXs. We could use, if the acetylene was ever the starting point, we could use either side or both sides sequentially to alkylate. We could alkylate one side and then alkylate the other if we had started with acetylene. And reactions like that above result in carbon-carbon bond formation, which is unique in the organic chemistry world. There are only a few reactions wherein we make carbon-carbon sigma bonds, and they are thus valuable. Well, that's it. We'll have one more video discussing all the similar reactions of alkenes, alkynes to alkenes, but this was that one reaction that's dissimilar, that's different. Bye-bye.